And thanks for coming. We're very excited today to welcome Dr. Joseph Berry as our second physics colloquium speaker for the spring semester. Dr. Berry is a principal scientist at the National Renewable Energy Laboratory. He graduated from the Penn State Department of Physics, receiving his PhD for work on spin physics of magnetic and hybrid semiconductor systems. After his PhD work, he was awarded a National Research Council Fellowship at the National Institute of Standards and Technology in Boulder, Colorado, where he developed high-resolution spectroscopic techniques for solid-state electro-optical systems. Since joining NREL in 2006, he's worked on a range of next-generation optoelectronic materials and devices with an emphasis on relating basic interfacial properties to device-level performance. His research interests have led to his current work as team lead on metal halide perovskite solar cell systems. He's also a lead in the DOE Center for Hybrid Organic Inorganic Semiconductors for Energy, examining spintronic behaviors in metal halide perovskites and relating these materials for applications beyond photovoltaics. Finally, he's the director of the U.S. Manufacturing of Advanced Perovskites Consortium, a collaboration between universities and national labs to meet the needs of U.S. companies examining commercialization of metal halide perovskite-based technologies. And Dr. Berry has given us permission to interrupt his talk with questions as they arise. So please feel free to drop your questions in the chat or utilize the raise hand function. We'll be monitoring both features for your questions, and we'll also have time at the end for more discussion. So with that, let's give a warm virtual Berkeley welcome for Dr. Berry and his talk on making metal halide perovskite photovoltaics a reality, an update on state of the art.
Well, thank you, Hannah, for that very nice introduction. I am on Twitter, mainly just technical stuff. And I will also put a plug in that the US MAP has a seminar series where we get to hear from some of the different company leads about kind of technical issues that they undertake related to, at the moment, mainly metal halide perovskite photovoltaics. And then I won't probably get a chance to talk too much about the activities in this center, but we're really looking at kind of basic physical properties of hybrid semiconductor systems. And you can check out that work actually on the website. And I'll have a link, I believe, later in the talk. All right, now if I can advance. So I will always like to start off these talks by acknowledging, that I've got a really great set of collaborators that I work with on a routine basis. And here's a picture of many of them. Additional people are listed here, but we have a really, really great team, both at the National Lab. We have some refugees from Stanford that we've taken in most recently. Both Mike Toney and Laura Shalas, who were at SLAC, are now also both in the kind of Boulder Golden area where NREL is located. And of course, the work that I'll be talking about today is mainly funded by the U.S. Department of Energy's Solar Energy Technology Program, or CETO. But we do get some support from the Department of, from ONR and the Department of Energy's Basic Energy Sciences Division. So with that, this is a colloquium, so it's important to acknowledge that while I'm a physicist and I tend to think the way physicists think, there are a couple different ways that we think about harvesting solar energy. There are solar fuels, which is kind of direct conversion of sunlight into chemical bonds. And then there's also concentrated solar power, where this is kind of what these types of systems look like, heliostats, where you take the solar energy, you concentrate it, you heat something up, and you can run a turbine. There's some nice kind of applications there where you can use those turbines, also fire them with fossil fuel and affect things like dispatchability. But then there's photovoltaics, which is down here, and that's kind of what I do. And as a semiconductor physicist, right, photovoltaics are kind of the nicest way to do this, right? You're taking direct photons from the sun, you're converting them into electron hole pairs, and you're basically harvesting them. So when we do this kind of activity, right, as we'll discuss in a little bit of more detail, the fundamental aspects of it are pretty straightforward. I would certainly argue that the most technically sophisticated, because semiconductors, and again, semiconductor physicists, semiconductors are cool. But there are challenges, and there is a perspective that solar technologies more generally encompass things that include uh, the elements you need to do dispatchability. That would be kind of time shifting uh, of energy resources, things like that. Then there are also these questions around, say, durability, right? You're making a semiconductor device; it needs to basically perform outside over extended time periods, and so there are elements of systems that need to address that stability and durability question. And then there's the grid infrastructure. And again, that goes to dispatchability in the same way that storage does. You need to be able to move power around and do things like this. And of course, as physicists, right, it's true that solar cells only work when the sun is shining on them, but the sun is not just shining during the day, right? We all know this. The sun shines all the time. It's just that we don't have essentially the azimuth to basically collect that energy. Um, a thing that was pointed out very nicely, I believe, in a commercial by a large multinational, the notion of solar cells in space, which is apparently a thing. Um, so in terms of the research that people do when they're looking at photovoltaics, the device physics, there are some things that we want to understand there. And there are certainly quantum-based approaches that tend to go to strategies that allow you to essentially circumvent the detailed balance limit for performance. And then there are new materials. And then there are these system level issues that affect things like inverters, right? How do we basically take DC, hook it up to our grid? But new materials is really where I spend most of the time, along with most of the folks in my team, looking at things. So this is what is affectionately known around NREL as the chart. This is the chart of best research cell efficiencies. And you can see that a lot of these technologies have been around for a long, long time. The technologies that we're going to talk about today in a little bit more detail are ones that really weren't a thing when I started at NREL in kind of 2006. But again, since solar cells in these kind of PV systems, all the ones represented on this chart, they use conventional device approaches. So none of this quantum physics-based approaches. That means they're really semiconductors, right? All of these technologies are based on semiconductor absorbers, and that's indeed how we categorize and name them. So it's a semiconductor problem that we're trying to do in solar cells. And the first rule of semiconductor physics, especially in the context of hetero interface-based structures, like most of our solid state electronics are these rules dropped down by Herb Kromer. And Herb Kromer's lemma: if in discussing a semiconductor problem you cannot draw an energy band diagram, this shows you do not know what you're talking about. And the corollary is, of course, if you can draw one but you don't, then your audience won't know what you're talking about. So this is essentially the basics of how a solar cell works. You absorb light, you create an electron hole pair. You can certainly, now of course you must excite above the functional gap, the electronic gap here, but then you can thermalize down to the band edge, and then the goal is to basically extract these carriers before they recombine out and essentially harvest that energy. So you can essentially put timescales on, and this is a diagram that we put together for a paper a few years ago, where you can actually look at the different timescales. So while conceptually this is all very straightforward, there are some things that we want to do in terms of making sure that the rates at which these different processes happen are matched up in a way that allows us to maximize the extracted energy. So in this particular device, it's a PIN device. We've also built in some critical components at the interfaces that allow us to preclude an electron, for the most part, from going in the wrong direction and resulting in loss in the system. But at the end of the day, the goal is to minimize recombination and maximize extraction. Not terribly surprising. The devil, of course, is in the details of how it is we do this in any one particular system. Now, the other thing to say is that, right, the choice of how we pick a semiconductor to do the solar task and to perform as a PV is very much a compromise, and we really kind of have to, right, we're kind of stuck with the sun that we have. If you think about what is possible if you had a narrow band illumination source, right? So if you think about a detector where you only need to detect kind of a single wavelength of light, you can detect at much higher efficiencies than what we can harvest this solar spectrum. Because if we go back here, right, by setting this band gap, we are a priori not collecting some of this radiation. And if we, make the band gap very, very narrow, while we will enjoy more photogenerated electrons and holes, the voltage that we can extract them with will be limited. And that means that the total power will essentially be capped. So a lot of what we do in designing PV systems revolves around making the appropriate compromise between how wide or narrow we make this electronic gap, and then how well we do at these interfaces in ensuring that every carrier that's photogenerated is harvested. So in that sense, it's a fairly straightforward and simple activity. And if you look at the thermodynamic limits, or the detailed balance limit, this basically puts a cap on how efficient you can extract this spectra depending upon what your electronic gap is and what the trade-off is. And if you look at things like silicon, which are well-established technologies, or gallium arsenide, which is really kind of the best semiconductor for the solar task from a number of different perspectives, you can see that there's quite a bit of headroom, and a lot of this loss is, due to practical considerations, because you want things like wires to transmit the photogenerated carriers and things like this, and that ultimately does limit your device performance. But again, if you think about what these devices look like, they're diodes, and this is a diode characteristic in the dark. And when we essentially illuminate them, we create the photogenerated carriers. If we operate this with no bias, right, we can essentially get this, and we short the leads on the device, we'll get this extracted current JSC. In contrast, if we go to the voltage, this is essentially the photo-generated voltage that we can see in the device. When we essentially, have all the photo-generated carriers, they have nowhere to go, so they'll create a maximal kind of voltage in the system. Again, this is indicative of kind of the losses that we see in the system. But if we want to actually operate it and collect energy and maximize the power, we want to be at this point here, which is the maximum power point, which is kind of the compromise between, extracting current and voltage out of this device. So again, this is all kind of, PV physics 101. But then the other thing we can do, right, since, one junction, we clearly have to make some compromise between, where we harvest and where we let photons through. It makes sense that one way to maximize the efficiency is to not make the compromises in the same way, but have multiple essentially subcells, right, that would pick off each different wavelength. And here you see a triple junction system where the top cell collects the blue, but it passes the shorter wavelengths. You have another absorber behind it that's picking off the green. And again, the shorter wavelengths still go through, but then you pick those off as well. And using this kind of approach, you can essentially increase your performance considerably. And indeed, if we look at this chart, if you want to be at these kind of efficiencies that I've highlighted up here in the purple, you have to kind of be in the multi-junction regime. In other words, you have to basically be splitting the solar spectrum up and letting each subcell operate very efficiently in a narrower gap. But of course, that means that your system is inherently more complex. And so there are always kind of questions in the context of how we can essentially harvest the maximum amount of solar energy, right? These are very, very big systems. How can we make those inexpensively and efficiently harvest as much energy as possible? And so, you jack up your complexity, and you have to pay essentially more costs and more expenses, particularly when it comes to materials like I highlighted here, which, while they're awesome PV materials on a per square meter basis, if you can afford a Bugatti, you could afford kind of, the kind of PV that has a triple or quadruple junction, and these power conversion efficiencies that would be up in these kind of 40% regimes. And it turns out if you're the NSA and you want to fly a satellite, that's actually a pretty good deal. But for most of residential homeowners, it turns out that's maybe out of reach. I guess is the right way to say it. So that's kind of the backdrop. And I've kind of skipped over the fact that there is one multi-junction down in here. This line here is a multi-junction line. This is a silicon perovskite multi-junction line. And this gets us to essentially where we're at with the metal halide perovskite systems. So can I ask kind of for a virtual raise of hands of how many people have actually heard of the metal halide perovskite absorber systems? This is something that, like, I got 3, 4, 7, okay. 8, 9, 10. Ooh, that's good. 12. All right, cool. So the metal halide perovskites, perovskites are very common kind of, it's just a crystallographic structure, right? I think the story I heard from Daryl Shalom was that something like 80% of the Earth's crust are basically oxide perovskites. I don't know whether that's actually true or not. I should look it up, but that's the story that I was told. In contrast, the metal halide systems are completely synthetic. We don't have a lot of halides around in our atmosphere, which is probably happy for us, but given the way we breathe. But these systems were first kind of examined by David Mitzi back in kind of the 1990s. This is one of the first patents that was issued for these kind of metal halide systems, where you have these organics and then you have these metal halide octahedra. Now, David Mitzi was looking at these for kind of transistor applications. But it turns out that these things are spectacularly awesome at doing the solar task. And this is something that, this was the first paper by Miyasaka, where they used these metal halide systems as essentially a solid state die for a die cell, right? And in this system, they got, a relatively modest performance of a few percent. There is an urban legend around NREL that one of the authors came to, one of the folks at NREL and said, hey, you should really look at some of these systems. And the question was, well, what's the efficiency? And the answer was, well, a couple percent, which was not as good as state-of-the-art organic cells at that time. And so they were told, well, no, come back when, it's over 10%. Well, that happened in relatively short order, as it turns out. But one of the other fabulous things about these materials is that in addition to, having the kind of absorption properties that we'd want, they're highly tunable. Now, these ones that Miyasaka showed are essentially lead bromide and lead iodide based. And this is methyl ammonium in this particular case. And it turns out as we tune the iodide and bromine, we can actually quite nicely tune the electronic gap. Not only that, this methyl ammonium, which was the one shown by Miyasaka, can be swapped out for cesium or formamidinium, and again, gives you a nice tuning of the electronic gap. So this is very analogous to what we love about kind of the 3,5 compound semiconductors, right? You can alloy gallium, aluminum, and arsenide systems to basically change the electronic gap kind of to whatever you want between the bounds of those endpoint compositions. And you can move to the phosphides to get even kind of more bandwidth, but there's some, there are of course some considerations there, but you can kind of do that. In these systems, you again have that same kind of tunability. And here you can see this really nice tuning of the energy gap. And this was work that was done by Giles Eperon and Henry Snaith's lab in the 2014 kind of timeframe. So, the perspective at a place like NREL, as I kind of indicated, is that if you want to be a real PV, a real photovoltaic technology, you need 3 things. You need to be stable, you need to have high performance, and you need to be manufacturable. Now, performance, I've just kind of shown you, right? When these things started, and again, when I started in 2006, these were not a technology at all. Since the first point on the chart, which was at kind of, the I guess it was around 14% level, current state of the art is at 25.5%. That is better than any other thin film PV technology at the lab scale. In addition, given that we can basically do this tuning of the electronic gap, the thing that's kind of cool here is that that means that there's an opportunity, just as there is with any kind of tunable semiconductor, to make multijunctions and apply those multijunction strategies, which means that you can essentially make existing technologies better if the band gaps are appropriately matched to maximize the efficiency. And indeed, in the last couple of years, people have worked at pairing these perovskite materials with silicon, and now you have a silicon solar cell device at 29.1%. Actually, this is out of date. I apologize. I didn't update this, but I believe it's now 29.5 is the record. And this is an efficiency that you will not achieve with a silicon cell alone. And that's kind of the requisite thing. If you're looking at a tandem architecture, you can't add that additional complexity, that additional cost that's associated with it, unless you can beat the single junction, right? Otherwise, it's hard to rationalize it. So it has the performance. And then the other thing that I haven't really told you yet is that all these points for the single junction perovskite are based on absorbers that are solution processed. And this begins to address this question of manufacturability. And then that leaves the question of stability, which we'll get to in a little bit. But at a fundamental level, right, when we think about things like semiconductors, everybody's done the tight binding kind of calculation or the nearly Fourier electron approximation for what band structures look like. But we know that the periodicity is the thing that's kind of the magic that creates the bandwidth. There are things like amorphous semiconductors that are kind of exceptions to this rule, but and in that case, you're still relying on a lot of orbital overlap to create the bandwidth in these electronic states. The thing that's interesting about the hybrid systems is that they are very much like traditional semiconductors. But when we start thinking about the defect structure that they'll have, they're very tolerant of a lot of defects. I mean, the question of defects in a semiconductor is kind of the prototypical problem. And, there's all kinds of defects that we'll worry about. It's also the reason why, if you think about systems like the 3-5 compound semiconductors, the reason why they're so expensive is that in order for you to get these very high performances that I showed on that chart, they need to be essentially functionally single crystal systems, right? They need to be perfect. Everybody needs to be in their place. There can be very few defects like I've just outlined here, like vacancies, impurities, interstitials, dislocations, and so on, right? I mean, impurities are a key functional property of a traditional semiconductor system, right? They allow us to do things like doping, for example. At the same time, we also have these kind of things like surfaces. Well, the metal halide perovskite systems, they're solution processed. The resulting materials are not single crystal. They're horrible polycrystalline messes, but yet they have these efficiencies that beat all the other thin film materials. And so the question is, well, why? The property that they have that's kind of unique is the property of kind of defect tolerance. As I just kind of laid out, when we have these kind of defects, particularly things like dislocations and vacancies, typically what will happen in a semiconductor like silicon is that you'll create deep states inside the electronic gap. Now, in the context of what we need to do for a PV system, that means instead of essentially being able to extract these carriers, right, we're creating pathways for additional recombination that undercuts our efficiency. And indeed, if we have a lot of these, we'll turn a material that's a reasonable semiconductor absorber into a hunk of garbage, basically, as a material. However, in the case of a system that we would consider to be defect tolerant, then, right, as we have in the metal halide perovskites, instead of having states that are deep in the gap that enable recombination, when we create a vacancy or an interstitial, the location of these essentially defects ends up being either in the conduction and valence bands themselves, keeping the electronic gap very, very clean, or they're very, very shallow, right at the band edges. these are some calculations, and it turns out there are some deep defects that we can make in a lot of these metal halide perovskite systems, but it turns out they're very hard to make. That is to say, their formation energies are quite high, so when you put them down, they are not the predominant defects that you essentially realize in a film. So when we talk about things like, especially this prototypical methylammonium lead iodide system as defect tolerant, that doesn't mean that there are no defects. And it doesn't mean that the defects that we have don't matter at all, but they don't essentially undercut the fundamental functional property of the semiconductor that we need for it to be a good PV absorber. So they do not destroy the functional property. There are maybe some other knock-on effects that we need to consider, particularly in the context of the metal halide systems. But this defect tolerance property is not something that's purely kind of theoretical either. You can actually go in and see this, and this is some work that we did a number of years ago where we actually hit and exposed with X-ray radiation a methylammonium lead iodide system, and we simultaneously monitored the essentially composition. And as we exposed this, we could see the lead we could see essentially the composition of the lead to iodide ratio of this move away from kind of the MHP PV, right? This was actually a little bit substoichiometric. I think it like started at like 2.9 or so, maybe 2.85. But we can see it essentially changing. And it's not until we get to 2.5 that we actually start seeing a kind of clear difference in the valence band edge of the material. In other words, we're creating lots and lots of defects as we're changing the composition here, but it's just not doing anything to one of the key functional properties. Now, it turns out one thing that we aren't looking at here is the conduction band. This is really just the valence band. And it turns out a lot of the defects that we create here actually are theorized to be essentially in that conduction band right at the band edge. So we're probably making the scattering, right, within that material worse, but we really aren't creating deep levels, and we really aren't changing the electronic gap until we get to a really, really high defect density. So the other thing you have to obviously have is you have to have a strong interaction with light. This is some work by DeWolf et al. Early on that show that you clearly have really, really strong absorption for these materials. You also have this fraction of the detailed balance voltage maximum, right? So you can imagine that in the context of this kind of band diagram, the maximum voltage you could extract would be equal to your electronic gap. So if you have a value of 1 here, right, that's to say that your voltage that you produce is maximum based upon the detailed balance limit for the band gap that you have. And this compares a number of the different solar cell technologies, and just as you would expect, things like gallium arsenide, gallium indium phosphide, which are perfect single crystal thin film systems, they do very, very well. But what's remarkable is the perovskites are very, very close in terms of this figure of merit, despite the fact that they're these horrible polycrystalline messes, which is kind of a amazing and fascinating thing. Now, we have the defect tolerance, but we can mess it up, right? Most notably, if we move away from lead and we go to things like tin, in this case, we're using that destruction of the defect tolerance as a functional tuning knob to basically change the electronic gap. But we're also creating essentially a lot of other defects that have low formation energies that are readily accessible. Particularly in the case of tin will want to basically create a vacancy and will want to p-dope the layer. And this is a diagram from this paper, some collaborators at NREL, where they calculate this and they show how these kind of bonding anti-bonding sites are changed as you basically alloy in the tin, and it basically changes which orbitals are functionally governing the electronic gap in the system. But we can use this as a nice tuning parameter, but we are basically destroying some of the defect tolerance as we do that, which is why lead is magic in the context of the solar perovskite materials. If it doesn't have lead, we tend to not think of it as a solar perovskite at NREL for the most part, which is something I'm happy to talk about. Lead is a great thing in the context of this. So this defect tolerance is really one of the things that has enabled this quick rise, right? I mean, certainly we'd like to think that we've learned a lot about how to put together thin film solar cells, and that's contributed to the fact that this line is, moving at the rate it's moving. But this defect tolerance is really the thing that enables this to have been achieved with solution processes. Now, this goes to this question of manufacturability. And one of the reasons why we're super excited about these systems, in addition to just their raw kind of performance. When we talk about manufacturing, we used to talk a lot about scaling at NREL, and that's the translation of small area cells to big area cells. But manufacturing is really more than that, right? It's not simply making things big. It's making things right and making them the same all the time. And it's making them very, very fast. And it's making lots of it, right? So it's all these things together. And that really means that we need to understand a lot of stuff that's happening when these things are formed together. But again, to date, all of these kind of records are coming from solution processes. And here what I'm showing, this is a facility at the Kodak plant in Rochester, New York, that is a target for basically producing metal halide perovskite solar cells. And if we can do this with these systems, this footprint, while it's not a small facility, would represent over a gigawatt, maybe as many as 2 gigawatts a year production in relatively small footprint at relatively low capital cost in comparison to something like a silicon plant. Silicon is roughly $1 billion a gigawatt. So this high volume manufacturing, we talk about gigawatts from your garage. If you have a garage this big, you're doing pretty well, but you still get the kind of point. There's also the opportunity, aside from kind of these applications where I work mainly for the CETO office, and so the CETO office has ground mount utility scale PV, but you could imagine also using the same kind of approaches to do kind of custom racking and mounting that would basically allow you to fabricate solar panels on site at the different aspects, say, of a roof to fit a particular site. But the notion that we can really use these print technologies to go very, very fast means that the opportunity to address kind of terawatt scale challenges with respect to manufacturing is a much more reasonable thing. In terms of the growth rate of silicon and given the capital expenses, right, if we want to reach 25 terawatts of electricity production by PV, at current production, it's over 170 years, right? This allows for some growth that's kind of predicated on non-exponential growth given the maturity of the technology. In contrast, for a modest 15% perovskite solar cell, if you consider the daily circulation of the top 10 US newspapers in their area, you could get to this kind of 25 terawatt scale in kind of 3 years. Now, that presumes that you can do things like produce the substrates and everything else that you need also at that scale. So I'm not saying that it's entirely straightforward, but there are orders of magnitude difference between these numbers, and that's indicative of the fact that we can use these additive manufacturing processes at scale. And we talk about some of these kind of considerations here. Plus, in this number, I'm not accounting for the fact that we can, again, take existing PV technologies and take them from, say, 19, 20% technologies up towards 30% plus, which is another opportunity. Oh, and this is one of our graduate students who's since matriculated and is now leading some of the efforts at MIT. DAC, this is actually a perovskite printed directly on glass that we did in our lab a number of years ago. So these are actually tractable things. Now it turns out when we're working with different companies, while utility scale is kind of commodity PV, there are a lot of other applications that we can think about for PV that are higher value that allow kind of different entries to market, right? And are also kind of related to this manufacturing aspect. Here's Lance Wheeler, one of the folks at NREL. And here what we're doing is leveraging some of the phase transitions that you can essentially realize in these halide perovskite systems to basically use that as a feature to create a dynamic window effect where when the material heats up, it darkens, and it basically, it's a brown absorber that you kind of see here. And indeed, in the context of architectural glass, he's got to get this figured out because it's brown, it turns out, isn't appealing enough. But maybe for sunglasses, smart glasses, I don't know, maybe. But that's what he's holding up here. We're also looking at lightweight applications because, again, these are very, very thin films. We can print them. And not only that, we can, in principle, make multi-junctions out of them. So things like drones are targets for some of our industrial partners. And then there are these ideas that I kind of alluded to earlier about solar cells in space, and then we'll beam the power down, right? Because the sun's always shining if we have access to it. So if we look at the solution processes that can be used for the metal halide perovskite systems, there's quite a range. I would venture to guess that all the points on the NREL efficiency chart are probably done with spin coating. But we have had good luck ourselves doing both the spin coating, doctor blading, slot die, ultrasonic spray. We haven't done screen printing, probably works, and inkjet. And we can make quite efficient devices using all these techniques. And again, this goes to the defect tolerance and what's kind of possible given the physical properties of the material. So this is a Nature Material Review that we did in 2018. And this shows basically the gaps between small area cells. And indeed, you can see this is old because, right, on the NREL efficiency chart, I showed you points that are in excess of where this maxes out. But there's clearly this gap, right, between going from a small cell to a larger area cell to indeed a mini module. And we can compare that against kind of other technologies like CAD-TEL, which is arguably one of the most successful the most successful thin film PV technology. And you can see that, perovskite solar cells really are kind of tanking off here. But this was 2018. This is the new chart, one of the new charts that the NREL I guess it's PV efficiency group has put together. And here you can see down here, this is basically the perovskite solar cell line for modules, where the size of the module is indicated by this coloration. And now you can see that, so this is where 2018 was, right? So this is where we were in 2018 in the graphs that I just showed. This is where we're at now. So that's a jump from 11 to almost 18%. And I believe, again, this is out of date because I know of at least 2 results that are at 18.9% for modules that are kind of in this 800 centimeter squared range, which is still small, to be sure, but is kind of what you would, that's a kind of starting point that if you can demonstrate that, you have an opportunity to go to these larger modules with, very few people making these extremely large modules other than First Solar and people like Hanwha. So I've shown you that we have the efficiency. I hope that I've just demonstrated that the scalability is something that is very, very rapidly being solved. And given the approaches that we can use, it looks very, very promising. So that leaves this question of stability, because nobody cares if you make an awesome device and it only lasts, 30 minutes, right? That's not going to be any good. But stability really is a monstrous technical challenge if you take a step back and just kind of think about it, right? We want to know where technology that 10 years ago nobody knew about, right, will be in another 30 years, right? That's the question that we want. So in other words, I want to know what it is that I can measure on my solar cell right now, right here in 5 minutes, that will tell me or allow me to forecast where it will be in 30 years, right? That's the magnitude of the material science challenge. Because if you look at how we've done this in the past, it turns out that for silicon and these other technologies, we really kind of just fielded them. Indeed, some of them maybe didn't have all the questions about stability sorted out when we fielded them. But we have now many, many decades of data on things like silicon modules. And there is there is and there are still challenges with basically making silicon-based PV modules that will last for 30 years, and with targets, kind of longer towards 50-year timescales. So this is this article that we did a few years ago now in ACS Energy Letters that was a perspective on kind of trying to understand how to approach this challenge that is stability in the context of metal halide perovskite solar cells. And I want to be super clear here, because it's not that we can't make devices that are reasonably stable. It's that, the solar cells that we make in our lab today versus the solar cells that we made in our lab a year ago are not the same, right? We're increasing the performance. And if you look at even silicon PV, as they try to improve the performance of HIT cells, they introduce new instabilities in those systems, not surprisingly, right? So those 30-year lifetimes that people talk about, those are predicated on having field data and then on having enough kind of insight and understanding about kind of what you're changing as you're chasing, say, improvements in efficiency, to make sure that you can still forecast where those devices will be. And even though, there's probably no other semiconductor we know more about on the planet than silicon, there are still opportunities to miss, right? There's still things that are introduced into silicon cells that, result in lifetimes that are not quite what we'd hope for them to be. So when we think about stability studies in perovskites, right, we have to ask some questions about what is it we're really trying to target and what is it we're really trying to look at. Because I would certainly argue, again, what we want is a time equals zero test that lets me forecast 30 years into the future, right? That's what I want, but that's a really hard ask. And if we simply say take the perspective, well, we're going to stress the system harder, right? If it gets 1 sun of sunlight outside, I'm going to make it 10. The question is that really stressing the same kind of mechanisms that are resulting in changes in performance over time or not? Which is, goes to this adage, right? When you heat an egg a little, i.e. in an incubator, you get one result, right? You get a chick. But if you put it in boiling water, right, which is arguably an acceleration of that process, you don't get a chick. And this is the challenge that we have with some of these materials. And then, knowing the future is hard. So again, trying to understand the details of this is really what's important. So we kind of proposed this kind of framework for thinking about it. And at the time that we proposed it, which is again a couple of years ago now, a lot of studies at the material level are really important and insightful in telling us about kind of the basics of things like, right, so we have the system where we have defects that are tolerated, but do those defects essentially allow for mechanisms that will change the band structure of our kind of prototypical PV device that I laid out in ways that we don't anticipate and which kind of undercut its ability to basically do the PV task? So these kind of studies are very, very important. Then there are things like operational tests, right? So we can make a device, because a material is not a device, right? All the interfaces and all the things that we put in together in the device stack have a lot to say about how stable or unstable a device is. And so you also need to be doing tests at this level, but then you need to go back and look at these things. And you can see that we didn't highlight these outdoor and IEC tests because at the time that we wrote the article, we thought, oh, well, those are like way, way off in the future. And again, this was maybe 3 years ago now. It turns out those questions are questions that we need to start asking now already, right? I mean, those are active kind of elements. And we need to basically be engaged with industry, which is why we formed things like the US MAP to begin asking these questions about how we address things that are happening even at the module level that go back to the cells, that go back to the materials, and round, so to speak. Again, in the context of some perspective, so the first practical solar cell, right, was reported by these folks in 1954. And, this is what the headline in the New York Times was, right? Or one of the taglines, limitless energy from the sun. It turns out the way they measured their efficiency you would not make it past peer review now, right? They did not do it legitimately. Unacceptable. And This is the most basic of measurements that we do for a PV cell, right? Photons in, electricity out. That's all you got to know, right? And that's very, very straightforward. But this doesn't account for everything that we see, right? We have standard test conditions. We don't account for things like solar kind of obscuration, right? So things like clouds. There are things like temperature coefficients, right, that change how the cell works as it gets hotter or colder. All of these things, including the variability of spectra when you change, say, your latitude or you change kind of other atmospheric conditions, all that stuff, it turns out we do address those things these days, but those are what we consider to be part of calculations of energy yield, right? If we're looking at a solar farm. They're not what we talk about when we talk about the power conversion efficiency of a cell. So we simplify it, right? The problem is that you really just can't do that when you're talking about these stability questions. There's just not an analogous kind of way to simplify it. And there isn't kind of a singular mechanism that we've been able to identify yet that tells you how the solar cell is really going to fall apart. So we can ask the questions of where the instabilities are. It turns out there are a lot of them. They're in many, many places. But it depends who you ask on our team, who which one we think are the worst. As the interface person, I always think it's always the interfaces, right? It's all about the contacts. It's all about this. But the folks who focus on some of the active layer formulation obsess about that, right? And then there are even the questions about kind of how you would package these things up. I will argue the interfaces, because it turns out a lot of the innovations we've done have resulted in improvements in stability are at the interfaces, but that's also because my colleagues have already taken care of a lot of the instabilities in the active layer, if I'm honest. But I guess this is recorded, so I just don't show this to any of my colleagues. So we have done a lot of work in trying to understand the science of stability. And if you're interested in this topic and trying to come to terms with, how to think about particular mechanisms that may be impacting your solar cells, I would recommend this review article that a graduate student who works for me, Sean Dunfield, wrote, that's in Advanced Energy Materials, where we really kind of walk through what current state of the art is, and with respect to mechanistic understanding of how solar cells that are made on these metal halide perovskite systems have changes in performance, right? What's really kind of at the root of some of those things. But this is a set of data that I think is kind of instructive. So when we started our metal halide perovskite work, I guess it's almost 6 years ago now, this is what we got for stability. And you will notice that the time is measured in 25 hours, right? That's not going to make a product. But we realized some things about the contact interface, and we certainly got better at making devices, because you can see the statistical spread was reduced. But again, these devices died relatively rapidly. The active layer people, right? You'll notice I went from this prototypical MAPI to this triple cation system, which is basically a combination of methyl ammonium, formamidinium, and cesium. And we made slightly better devices, and they lasted, we could at least measure them for long periods of time, right? So now we're at 150 hours or so. And we made some additional improvements to the contacts, which is why I think contacts matter. And you can see that we significantly improved our stability. We still have suffering from this initial burn-in, but we're advancing. And then we made some additional changes to that contact, because here, while we changed the organic transport layer, we went back to gold. And when we moved away from gold to this moly aluminum, we again made things significantly better. And then finally, when we took away the titania, we made yet another change. And this is essentially operational data for a metal halide perovskite solar cell operating in ambient lab conditions without any encapsulation. And on the one hand, it's only 1,000 hours. On the other hand, I would argue that we've understood kind of fundamental things that we targeted when we made each of these changes about the interfaces, and to a certain extent about the active layers, that pushed this stability over more than 3 orders of magnitude by understanding what was going on in the device and addressing it. And we were subsequently able to show, so this was reported in Nature Energy a few years back, quite nice performance for quite nice efficiency devices at that time. And not only that, we were able to show that while the active layer was important, and again, this is why I have this skewed perspective, since the interfaces are kind of my gig, we're able to make devices that have really quite nice stability across the different active layer compositions, which means that we can tune the electronic gaps around and still maintain quite nice stability. Here, we are basically keeping water and oxygen out, which are known degradation mechanisms, in contrast to this data where we let water and oxygen kind of have at the active layer, which is a known source of degradation. So we were really able to do this quite well. And then this is some data that we've subsequently essentially validated for a little bit over 5,000 hours, so just under 5,000 hours. That's right, because it turns out making a 5,000 hour test is challenging because things like the lights go off. We'll lose electricity in thunderstorms and stuff, and that will impact some of these tests. But we made it 6.5 months, and we subsequently validated this data with follow-on studies where we were able to get to a full 5,000 hours and get very, very similar results in this particular device architecture. Subsequently, we've also gone on and tried some very similar approaches to essentially contact engineering in slightly different architectures to realize, again, similar performance if we take on the similar kind of considerations about the details of the interfaces. Now, when we want to make these things really big, it turns out that one of the things you do is you make cells into mini modules, and you introduce a lot of uncontrolled interfaces from the perspective of this last paper. So that's one of the current projects we're working on, is basically making these kind of devices where we're introducing scribes and subcells and things, but still trying to maintain control over the details of the interface and not allow things like these kind of mechanisms to impact on the solar cell stability. Yeah, this is just kind of the laundry list of a lot of the stuff that we've done related to these topics. And I guess since this is being recorded, you can have a look. It's a lot of work, but one of the things that I think the team is super proud of is the fact that you can clearly see links in our work as we move through the activities. In other words, most of the stuff that we do builds on the previous results in a way that's rational and that makes sense, and that provides a level of validation for the science that we think is underlying that. And I think that's an important aspect of kind of how we try to transition things from the lab into a real technology. All right, so I'm at an hour. The last thing I was going to say is a little bit of word on tandems. So it turns out that at a place like NREL, we have to be kind of good at solar cells. And I would certainly argue that if you're good at making a single junction solar cell, that is the prerequisite to making a tandem, right? If you cannot make a good single junction cell, then the hope of putting two of those together in a way that's more than the sum, right? I mean, that's a challenge. But we are looking at all perovskite tandems. And at the moment, actually, I'm going to probably just go to the next one. If you look at what state of the art is, right? I mean, so 25.5 is pretty good tandem, right? Here, the silicon perovskite is a pretty good number. So a tandem's got to be pretty good. But the silicon perovskite tandem is, well above this one, right? So we can add really, really good solar cells that have taken, all of the learning curve from all the silicon technologies over the years and really kind of pushed it farther. But this is where we're at in terms of state of the art for all perovskite tandems. We just had this paper, which is kind of a practical guide for considerations of putting together all perovskite tandems. Joey Luther is really awesome at coming up with really catchy names. So it is really a choose your own adventure kind of article. You can see how, and we walk through choices made in the first subcell, how that will impact choices made in the second subcell. Because as I mentioned, most of the highest performance across electronic gaps are all made from solution processing. Not only that, they typically use common solvent systems. So if I put down my first subcell and don't protect it appropriately, my second subcell will wipe away my first one. And so one of the key innovations that we've done at NREL is come up with essentially a recombination layer that allows us to process from the same solvent systems 2 cells back to back in a way that allows you to get very, very efficient devices. Because of the time, I'm not going to talk too much about it, other than to say that we haven't quite gotten over the 25.5 of the single junction metal halide perovskites device, but I do anticipate that we will do so in the next several months. I have a lot of slides about kind of like, 4-terminal, 2-terminal configurations. There's a whole lot of things we could discuss there, but I'll probably just go to final slide, which is to show exactly how horribly complex one of these tandem stacks looks like. Oops, sorry. This is our 23% tandem that was reported about a year ago. Like I said, I expect us to be able to overcome the current single junction limit in the next, we'll say, I would expect in the next 6 months. You'll see reports on that. So stay tuned to that. And with that, I'll just wrap up with some of our alumni who have gone on to bigger and better things. This is postdoc who worked with me, Philip Schultz, hanging out with the president of France, Macron. He's a big deal now. Philip is, now that he's left us. But also Jeff Christians, who did some of the work I showed, is at Hope College. Zhen Li has done a lot of work on some of these absorber materials. And Dong Hui, who has moved on back home to Korea, but we still collaborate on some of these silicon perovskite tandem work with. And yeah, you'll find me on Twitter. Here's the Choice C4C work if you're interested in things like spintronics, and then USA Perovskites if you're interested in understanding more about kind of what our current challenges from an industry perspective. So that I'll nobody interrupted, but they did participate in the poll, so I appreciate that. Hopefully it was okay.
Great. Thank you so much, Dr. Berry, for the great talk. We're kind of out of time, but maybe if we have 1 or 2 questions, you can raise your hand and we can unmute you. We have a request to go back to the putting things together slide from Giovanni.
All right, I have the technology. Putting things together. Was that not this one? Before this? Oh, here, yes. Okay, there we go.
Okay, is there a question here? You're free to unmute if you'd like.
I'm not looking at the chat, but I can do so.
Got it. The talk will be recorded and posted later too. Maybe I can ask a question about what exactly is it at the interface that increases the stability or the performance of the cell, and does it have to do with defects at the interface?
So, right, with all things semiconductors, it always comes back to the defects. And so it does, in fact, relate very closely to some of the, I mean, if you think about it at a very, very basic level, if you want to basically create a PN junction, right, or an abrupt heterointerface, you want to put the 2 materials together, but, and you want to create a large electric field, especially in the context of, say, a PV device. But if that electric field is too large, right, you'll drive chemistry. And if you drive chemistry, you'll create defects, and those defects will be recombination centers. So in the case of these metal halide perovskite systems, right, I didn't talk about it too much, but if you look at them from a kind of a basic kind of physical structure, these metal halide octahedra are relatively plastic, let's say, right? They tend to basically rotate and move around a lot. And so the opportunities to do chemistry there is pretty high. Plus, in the context of a PV device, it's not just the heterointerface we put together initially, right? We're gonna create photovoltages there that are gonna further drive potentially electrochemistry at those interfaces. So the electrochemical considerations there are super important. Here we showed, gold, or pardon me, silver iodide, right? I mean, that reaction's a mess, right? I mean, so if you put silver directly in contact with the perovskite, it's a mess. And halides, generally speaking, are quite reactive. So really, those are the interfacial interactions that we're trying to manage. If you look at gold, we actually did a really nice article with Barry Rand that came out probably, I guess it was just last quarter, probably in December. So early on, the folks at EPFL identified the fact that if you used a gold contact, and in that series of plots that I showed, right, when we removed the gold and went to a different contact, things got better. Well, they showed that gold actually was they thought it was electromigrating, right? So under the electric field, it was driving the gold through. It turns out we've looked at that, and it's actually an electrochemical interaction there. So it's not simply that the gold will migrate under the electric field. It's that once it comes in contact, the electrochemistry will drive it all the way through the active layer, creating a lot of horrible problems and creating essentially recombination centers inside the active layer. So that's one of the big things we worry about, is the electrochemistry of those interfaces.
Great, thank you. I think we have time for one more quick question from Cosmic. What is the efficiency for current purchase and install standard home and industry cells? And what do you think is the 5-year target for halide cells?
So you're talking about silicon, I presume, right? Since you can't buy CadTel.
Right.
Yeah, so I believe if you go to SunPower, they will sell you, I want to say it's a 23% module, something like that. Now that's a Ferrari kind of product, so it's not exactly right. I mean, for PV, you want it to be cheap, efficient, and stable, right? You only get to pick two, right? So SunPower is efficient and it's stable, but it's not cheap, right? It really doesn't hit the metrics that people talk about for silicon a lot of the time. If you go to something that's like a handwave Q cell kind of thing, or PERC, you do better on cost, but your efficiency is going to be lower. So for perovskites, are you thinking silicon perovskite tandems, or are you thinking all perovskite devices?
5 years, best you can do in a commercial market.
5 years, I would expect that we will be able to do, we're certainly targeting 20%, 20-year lifetime, thin film, single junction. There are people that are certainly looking at 30% silicon perovskite tandems. We'll see whether they get there. We do that stuff. But I would like to see a thin film perovskite, because I think with a silicon perovskite tandem, you will do better. You will be able to have a market entry, but I think that it doesn't address the terawatt challenge, because I think you'll have problems going to the kind of scale that you need. So I really want to do the other. And indeed, we have corporate partners who are in the thin film game, so to speak.
Thank you.
Great.
I have a suggestion. Liquid mercury as a contact. I mean, it sounds crazy, but maybe it would work.
I've heard worse things. I'm not going to say too much else about that.
If it's really, really sparse, I mean, if it heats up and it's dangerous, and it's a lot, and I can think of a lot of negative things. But I mean, I come from old radio days, and that would be like, What's an idea?
Like I said, I have heard worse, far worse ideas than that. Now, you might not want to go full like mercury, but there are other metal combinations that might allow you to overcome the electrochemistry. So and I'm probably not going to say a whole lot more, but it's an interesting thought for sure.
Thank you.
Great. Well, thank you again, Dr. Berry, for a great talk. Thanks everyone for coming. That concludes Colloquium. Have a great evening.